I'm starting an exclusive club, and you're invited to join, but only if the current members, all of them, get together, review your application, and achieve consensus. This is Data Skeptic Consensus, and it's the third installment in our series about how multi-agent systems achieve collective decision-making. In the case of my exclusive club, new membership is going to require not just a majority vote, but a unanimous vote. And that's naturally going to limit the size of how big my club is going to get over time. Mashbat Suzuki joins us today to help me understand what that asymptote looks like and some of the other interesting novel properties of a voting system like that.
So my name is Mashbat Suzuki, like the car. I'm a last year PhD student at McGill University in computer science and mathematics. And I'm supervised by Adrian Vera, and I'm from Mongolia. And I'm very happy to be here, and thank you for inviting me.
First got exposed to your work when I read the paper I invited you to come on and talk about mostly today is How Many Freemasons Are There? The Consensus Voting Mechanisms in Metric Space. So no less than 3 interesting ideas for me in the title. Maybe we should give some background to open up with. Consensus. What does that mean? Is that just the majority, or how will we be using the word today?
Consensus mechanism is a mechanism in which you have to select a candidate where only if everyone agrees on it. For instance, say you're running for some group leader, you get accepted only if everyone in the group agrees on it, and you won't get accepted otherwise.
So that's like unanimity then, yeah?
In here, yeah, it's basically the same as unanimity. But in different sort of settings, unanimity also implies that it's a property where you have, if everyone agrees on it, you get accepted, but something else can happen. If, let's say you can use different rules otherwise. There's a different sort of distinctions there, but it's basically the same as unanimity.
Yeah, and that particular choice leads to some interesting things, and you guys have presented this really concise analogy to the Freemasons. Well, I suppose getting down to the actual count of Freemasons, you're not trying to conduct a census here that just formalizes.
No, it's just a funny title to give because, as you know, that Freemasons are this interesting sort of group where you become a member only if everyone agrees on it. So it fits our mechanism. So they run their group through consensus voting.
Gotcha. So it wouldn't surprise me if, just given how much sort of folklore that surrounds the Freemasons, that there might be at least a few listeners confused about whether or not they're a real organization. Could you throw a few facts at us?
So they have amazing temples in Montreal. For instance, I live in Montreal. So they have a huge temple here and they're very active. And I actually don't know too much about them, their inner workings, or I've never been inside their doors, but they're very real. Yeah. You can go to their building in Montreal, for instance.
So real organization, and in terms of getting accepted into it, if I wanted to go in that building up there in Montreal, is this the actual mechanism they literally use, or is this a sort of an analogy?
So I don't know this for sure, but I heard and I read online that in order to get accepted, that everyone in that temple or everyone in that group has to agree on it. So it is the mechanism that they actually use.
Cool. Well, I guess whenever that started, it wouldn't be surprising that it could grow kind of quickly, right? If I was thinking of starting my own such organization and I first invited my wife, now we have 2 members and perhaps she and I can agree her sister joins and my sister joins, but at some point someone's going to say no to the next member. What can we learn about that and how do we study it? What are the interesting asymptotic questions?
So we have 2 different settings here. So one setting is that we model people's opinion, right? So when you say, I prefer my wife versus I prefer my daughter, or so on and so forth, we need to model the preferences of people. So one of the classic ideas in voting theory and actually just modeling people through machine learning or any sort of this setting is this parameterizing people's opinion or parameterizing people. So for instance, let's say you could be left-leaning, like politically left or right. So there's a spectrum for which you are lied at. Let's say you can be at the center, or you could be at the very right wing, or you could be at the very left wing. So we can model that as any number between -1 and 1. Let's say 1 being the right wing and -1 being the left wing. So then that's one example of how you parameterize people, right? Because we want to study this rigorously and mathematically. So we need a method to represent people. And our model is that, okay, so if you have this space in which you're represented, you're in Euclidean space, and some point is you, your opinion, and you vote for someone who is similar to you. So let's say if you're very right-wing, then if some candidate comes in, let's say, then you're more likely to vote for someone who is right-wing than left-wing. So someone who is closer to you in opinion or characteristic. So that's our model of voting. But this question was asked actually before in one dimensions, but in one dimension, so you basically just have an interval between -1 and 1. And this was actually studied by a very famous mathematician called Noga Alon. He has a paper in, I think, 2016 or 2014, I forget. But we did this in higher dimensions, in actually specifically 2 dimensions, because it introduces so much more complexity when you go up in a dimension, right? So for instance, why do we need higher dimensions is because before you were representing people as left and right, but people are more complex than that, right? You can't just represent a person by just one number, for instance. You have to use multiple features, as machine learning people like to say. So you have basically multiple characteristics of people, and they become the dimension. So we do this in 2 dimensions, and surprisingly, the mathematical difficulty of asking this question jumps huge. It becomes actually much more difficult in 2 dimension than 1 dimension.
Very interesting. And I guess maybe the answer is grounded in a lot of details, but is there an essence to what that challenge is? Is it that there are more simulations, or is there a complexity theory aspect of this? Why is 2 dimensions so much more difficult than 1?
So for instance, if you look at a random shape, you can characterize this consensus voting as looking at something called random convex halls or some random shapes. The question boils down on understanding certain random shapes. And here we're assuming that the candidates are appearing, let's say, uniformly at random. On the interval, you have existing group members. And if you accept somebody, then he becomes the group member and you evolve like that. So the candidates are uniform at each sort of time step. And so to answer the question, when you're looking at these sort of random geometric shapes, in 1 dimension, there's only one shape. It's just an interval. Any convex shape in 1 dimension is just an interval. It's some number between, let's say, it could be -0.5 to maybe 0.1. It's some interval. But let's say if you go into 2 dimension, all of a sudden there's so many different shapes, so many different things that can happen. If the shape is convex, or even just not convex, in 2 dimensions, there's infinitely more complex sort of shapes you can get. Because in 1 dimension, you only have an interval, but in, let's say, 2 dimensions, you have n-gons, you have triangles, you have something that approximates your face even. That could be a shape in 2 dimensions, but that's not going to happen in 1 dimension.
Makes sense. I'm trying to, I guess, imagine how this dynamic system will evolve. Your idea that in however many dimensions, all current members are going to vote for people that are similar to them. That's intuitively pleasing, right? It seems like a nice model. And I'm trying to brainstorm how will that play out. And my instinct tells me that the best candidate then is sort of at the centroid, and that we'll have, since it is a strict, even one person says no, you're out, that we'll have very middle of the road future members, and that'll be sort of self-reinforcing. How does that align with what actually happens?
That's exactly the opposite of what happens. So in this very strange model, even though people are voting for someone who is most like them, what you can show mathematically is that people who are more at the most extremes are the only guys who get accepted. So that's the very surprising thing about this, is that it's actually very counterintuitive that even though people are voting for someone who is most like them in terms of these candidates, the new candidates at, let's say, in the 100th time step, the new candidates are actually very, very near the edge of the space. So they are the extremes. What you get out of this is actually very interesting, is that if you sort of let these very exclusive social groups and let them evolve in this very natural manner, then the new members are more and more extreme.
Very interesting. And that extremeness, is it sort of, I guess I want to ask, is it uniformly distributed, even though I'm not sure what space I'm talking about?
Let's just take a square, right? Like 1 by 1 by 1 by 1 square in 2 dimensions. So in each time period, let 2 candidates appear uniformly at random. You have some group members, 2 candidates appear uniformly at random, and the existing group members vote for one of the 2. They vote for someone who is closest to them in terms of opinion or in terms of character. And you accept someone if there is a consensus, if everyone agrees to it. So now if somebody gets accepted, now he is a new group member, so he gets to participate in the next voting and so on and so forth. So the main assumption is that the candidates are uniformly distributed on this unit square. So what I'm saying by people, the new members appear at the very edge or the most extreme people is they're the new members closest to the vertices, like 1, 1 or 1, 0 or 0, 0 or 1, 0. And so this behavior also happens in 1 dimensions too. This also happens in 2 dimensions. So it is actually the exact opposite of what intuitively happens. You would sort of imagine, if people are voting for people like them, sort of you would have a distribution of the new members would be close to the center. But that's actually not the case. And this has an interesting implication because this says that as time evolves in this sort of very exclusive consensus voting groups, that extremism is the most likely outcome.
Yeah, it's a little alarming, I guess.
So I see this in sort of real life as well. In, let's say, if you're in a very right-wing group, then the newer and newer members, they don't become all of a sudden center. You know what I mean? If you start off right-wing, the whole group sort of becomes more and more and more right-wing, more and more extreme. This sort of thing, I think, actually happens.
So could I rephrase it? You tell me if this is fair, that when I'm saying I'm going to accept someone similar to me and then saying it's someone radical, but then to also say they're radical, seem at odds. But I guess maybe the way I could rationalize it or anthropomorphize it is to say, although they may be radical, the ways in which we're similar, we are extremely similar.
Exactly. So that's fair statement. And I think there's another big reason is that in that social group, if this new candidate who's not going to get accepted, if he's not radical, then you can always find some guy who disagrees with them. And it's this strange, almost this paradoxical thing happening. Even though, everyone has to agree on it, on you to get accepted, that the new members have to be near the corners. Because anyone can veto you. And only way that you're not going to get vetoed is essentially these two candidates are so far radical that the group has to accept only one of them. Because if they're both really radical, and it's actually more likely that there's a consensus.
Gotcha. And if I have two radical people, I guess they would even split the vote or have some ability to split the vote. It's the unanimity that really draws this out.
Exactly. So what you were saying is that people are more concentrated towards the center. That happens in majority voting. But in this unanimity or consensus setting, that does not happen.
Gotcha. And with that hard constraint, another important aspect of the work is the asymptotic trends over time. Could you share a little bit about the growth of these groups?
So this is another very surprising thing that we have found is that the behavior of these groups change drastically depending on which space you're looking at. So as I was saying, right, if you're looking at the square, if you parameterize people to be on the unit square versus if you parameterize people to be on the unit ball or unit disk, then the behavior of the group are completely different. It changes the whole thing, whole behavior, whole dynamics of the situation. And what we found is that there's an exponential separation between the two. So on the unit square, as time goes by, as time increases, you have at most log t times log t, essentially log t members after t time periods. But on the unit square, you have polynomial number of group members, which is in expectation, of course, which is t to the 1/8. And in computer science, we look at these exponential gaps very often, and it's very surprising to me that you see this exponential separation or exponential gap between the two. That if you model people as coming from a unit ball versus a unit square, you get drastically different dynamics and drastically different behavior of the group and drastically different sizes of the group asymptotically as it increases.
I was wondering if we could maybe unpack the geometric explanation a little bit. I know not every listener is comfortable with hypercubes and this sort of stuff. When we're describing people on those spectrums, what does it mean maybe to be somewhere, perhaps we could frame it in terms of like, should taxes go up or down? Would that be the 0 and 1 points?
That's a great way of saying it, right? Let's say the y-coordinate would be, what percentage do you think the taxes be? If your y-coordinate is 0.15, let's say, then you believe that whatever, the sales tax should be 15%. And if your x-coordinate would be left wing versus right wing. So, and the y-coordinate would be like a tax or something like that. So suppose you're a left-wing person who thinks that we're not taxed enough and we should be taxed 40%, then you should be, let's say, minus 0.5. And if you think the tax should be 40% and be 0.4. So we are representing a human as these two features or two numbers.
And would you say that it's an approximation? Obviously, everyone is infinite dimensional vector, I guess, if we all want to feel unique and innocent, right? But I guess how big of an assumption is that to say we need to take the first two eigenvectors or whatever we're doing, but compress our description of people into two values?
People obviously can't be expressed by two numbers, but it's something that we can do. We have to approximate because the real world is very complex and we want to do a best approximation that we can. And that's one way of sort of approximating people. But as you say, right, if you increase in dimension, you get more and more accurate representations of people. But at the same time, people really do more actually help. Like if you have million dimensional space, you have to ask million different questions to pinpoint where that person is at, right? So maybe asking just two questions is enough. Are you left wing or right wing? And how much taxes should be? Or any sort of two important characteristics is maybe enough. Basically, two is the best we can do, yeah. But I don't think it's very realistic. If you're asking if it's realistic, we have to do some studies, but it's not very clear to me if it's realistic or not.
Sure, yeah. And I mean, it's sort of very appealing to say, 3 would be better than 2 and 4 would be better than 3. But at some point, there's diminishing returns. It depends on what we want to inference from the system, I suppose.
Exactly.
So the proofs are really great. I'm going to refer people to the paper. It's a mathematically dense and wonderful read. I don't know that we're going to go through line by line on any proofs, but perhaps we could have a quick conversation about some of the mathematical tools. Obviously, people should have a little bit of measurement theory. What are some of the other techniques you made good use of?
Our paper, essentially, the main technical difficulties is sort of looking at how these random convex halls evolve. If I may be a little bit technical here, so our consensus voting mechanism, what we first do is we characterize them in terms of these things called Voronoi regions. So people in maybe computational geometry and maybe some machine learning also know this, that the Voronoi regions is a tessellation of the space into sort of partition of the space into which points are closest to which points and so on and so forth. So we're looking at how these Voronoi regions behave with respect to these random convex halls. And this randomness, you may think it's coming from uniformity, but we have to transform the uniform setting into a different, when you look at the actual distribution of the winning candidates, that it's no longer uniform. And we have actually a difficult sort of mathematical obstacles that happen with random convex shapes coming from different distributions. That the distribution that is not easy to say. And so the main sort of mathematical technical contribution is describing how these random convex halls evolve. And I think that question on its own is very interesting. And I think one of the reviewers of my paper said that this question, just purely mathematical point of view, is also just a very interesting problem and question on its own.
Yeah, I think people who are interested in Hilbert spaces and that sort of thing, I believe, have a deep interest in this sort of work as well, even though it seems totally unrelated to voting in some sense, I guess.
Right. You can rewrite this paper just as a pure math paper and it would just be the same, because, computer science and this question arose from voting theory that we wrote it in this manner, but this could just as well be just a pure math paper.
And in terms of the mechanism, obviously the Freemasons are a great example. Are there other real-world use cases where this is the voting mechanism put in place?
So it's interesting, there's like some judicial verdicts I heard, and also Japanese corporate governance is one of them, and some religious groups like Quakers. Have you heard of them? Like there's a religious group called Quakers, and they also have this consensus voting or this unanimity voting system.
I had just discovered this in my research. Yeah, I knew of the Quaker religion not too deeply, but I'm intrigued to learn more about this.
Yeah, I don't know too much about them as well, but it's a sort of a branch of Christianity that I don't know too much really about. But it is said that through various studies that they make their group decision through unanimity. And unanimity or this consensus has good advantages over, for instance, plurality. Because when a decision gets made, everyone has to agree on it, so everyone's happy if a decision is made, right? Whereas in majority voting, it could be that half of them may not be happy, right? So there's advantages for consensus voting, and it is used in small scenarios and in some religious groups and some corporate governance scenarios. And I think our work could generally be extended to study more different sort of scenarios as well, not just voting theory.
Sure, yeah, that's interesting. Could you expand on that? That's pretty interesting. Where would the research go next?
I'm trying to develop this to more dimensions. The research, the next step would be to go from 2 dimensions to just any dimension. We have some partial results on that. And in our model, just from a technical point of view, that we said that candidates appear 2 at a time, but that can also be removed. But the analysis would just be horrendous. It would be a nightmare. But we can do that and say something about that. And I would also like to sort of look at some connections to learning theory, or if that's possible, like learning people's preferences, or can you sort of, so let's say if you're left wing and right wing, your tax should be here, and so on and so forth. Can you learn the distribution from just the dynamics? So we assumed that candidates are coming uniformly at random, but now if I've given you sort of just what happened in the voting system, then can I know how the candidates appeared, what the distribution of the candidates were? So it's questions like this, but I'm more sort of mathematically inclined. I haven't really thought super hard into real world applications yet.
Well, along that line, the paper is very mathematically rigorous. These are formal proofs. One could have maybe also approached this doing some simulations and just said, let's, write some computer code that randomly samples these.
I've done that, yeah. So to check that t to the 1/8 and this log t bounds were correct, this project took me 1 year. And a lot of the times where I just did this on a computer, wrote a Python script and let it run, and I was just looking at how the group was evolving, where the new members were going, and how this shape was looking like. And from there, I took an inspiration from the computer sort of model, computer experiment, and made a rigorous mathematical proof that is based on that.
Oh, very interesting. So good that theory follows practice, I suppose.
Right. Because it's hard to know. First, I did not know what the right answers were. And I realized this is actually easy enough to implement on a computer. And I saw that there's this huge different behavior, and this leads to different questions, right? I think in the world of computer science and mathematics that there's actually a lot of room nowadays to experiment with computers and try to get rigorous proofs using sort of inspirations from the experiments from the computer.
Yeah, it is an interesting advantage that some asymptote could be measured and backed into, I guess, or we get some good hints about where it's headed.
Exactly. It's a great hint, yeah.
Very neat. Well, Mashbat, tell me a little bit about where people can follow up, learn more about your work and things like that.
My paper is on arXiv. It's called How Many Freemasons Are There? The Consensus Voting Mechanism in Metric Spaces. And I will also give a talk at the 13th Symposium on Algorithmic Game Theory. Unfortunately, because of COVID, the conference would be online, but my talk, it would be recorded and it would be on YouTube after maybe mid-September.
Fabulous. I'll have links to the paper and the symposium and down the lines the video as well in the show notes. Well, Mashbat, thank you so much for coming on and sharing your work. This is really interesting.
Thank you so much for inviting me, and it's been great talking to you.
That concludes this installment of Data Skeptic Consensus. Our guest today was Mashbat Suzuki. Our theme song is Paradox by Odling. Claudia Armbruster is our associate producer, Vanessa Burciaga does guest coordination, and I've been your host, Kyle Polich.